היום אני אדבר על איך עושים language identification, איך אפשר לעשות את זה בבית, ואיך אנחנו עשינו את זה, ומה אפשר ללמוד מהתהליך. אז מה שיהיה בשיחה הזאת זה קודם כל למה אנחנו עשינו את זה, איך עשינו את זה. אני אציג את הבעיה של ה-language identification כבעיה של machine learning, כי אני מניח שלא כולם פה יודעים איך לעשות automatic speaker recognition. קצת דוגמאות על ניסויים אמיתיים ומסקנות של כל התהליך. טוב, אז קצת על גונג. גונג היא חברה יחסית צעירה, אנחנו רק 3 שנים, כבר 150 אנשים עובדים אצלנו, גייסנו מעל $70 מיליון. אנחנו מקליטים המון דאטה כל יום, גם וידאו וגם אודיו, והלקוחות שלנו מאוד מרוצים מה שאנחנו מספקים להם. כפי שאתם יכולים לראות בפינה הימנית העליונה, הצירו כמה הלקוחות מרוצים, זה מתוך ה-G2 Crowd. ה-G2 Crowd זה איזושהי פלטפורמה שמספקת אפשרות לאנשים שמשתמשים בשירותים B2B, להציג את הדעות שלהם על המוצרים שהם משתמשים בהם. יש לנו צוות יחסית גדול של החוקרים, אנחנו מעל 10 אנשים, וזה לא כולל את כל אנשי התמיכה והמהנדסים, ואנחנו פותרים כל מיני בעיות בכל מיני נושאים, גם בווידאו, גם באודיו, וכמובן ב-NLP. עכשיו, מה שאנחנו עושים זה משפרים את השיחות של אנשים. עכשיו, מה הכוונה? יש לנו, הלקוחות שלנו בדרך כלל זה אנשי מכירות, או צוותים של אנשי מכירות, או צוותים של הצמיחה. הם מקליטים את השיחות שלהם עם הלקוחות שלהם. אחר כך אנחנו נותנים להם פידבק, איך הם היו בתוך השיחה הזאת, ומה הם צריכים לשפר, מה הם לא צריכים לשפר, מה הם ממש טובים בהם. אנחנו משווים בין הנציגים. וואו, should I switch to English? Sorry. We compare between the representatives, and we provide actionable feedback for the people that use our system. So, how we do it? We use the Kaldi speech recognition toolkit. It's an open source toolkit for the speech research. And when I say research, it's research oriented because it has many building blocks that you can combine in the order you want to receive whatever you want. Like, see, you have a feature extractor, neural networks for acoustic modeling, language modeling, and all the stuff you can combine together in any combination you want. What is most important from the Kaldi is that they provide working examples from the publicly available data. So you can just download their example, press a run button, and you will receive some kind of model that works okay. It's not perfect, but it works fine, and you can start from there. That's what we're going to do today. They also provide some pre-trained models that they train on big amounts of data. So if you want just to find something that is just working for some kind of experiment or proof of concept, you can just download and run it. It provides good results. Sometimes it's state of the art. And if not, it's very close to. And it's written in C++, so it's suitable for production. So what's the problem we're going to solve today? Our customers have many languages they talk to, like French in Canada and sometimes in Spanish in South America. So they want to receive whatever they're doing with our program in English. They want the same in other languages. So in order to do that, we have to do some kind of speaker recognition. And building a single language speech recognition engine is much easier than doing something that covers all the languages. So what we do first, we need a language identification module that will switch the call to the suitable language recognizer. So we will use Kaldi LRE07 recipe for starting point. And Kaldi has a long list of all kinds of recipes. You just select the one that is relevant for you and just run it. So let's set our expectations. From the paper that is written by Limsy, it's a French institute, and Vocapia, it's a company that does speech recognition for as a business. We see what they have done previously in 2016. So we see two main trends. As longer our speech durations are, our recognition rates are better. And when we have several type of recognizer, we can compare them. So we have a phonetician, phonotactic recognizer that is known, aware of different phonetic labels that can be used in specific language. We have lexical recognizer here that is known about the vocabulary that is used. IVC is an I vector. I will explain it later. And RNN is a regular RNN network that remembers what was previously. So we see that if we use the I vector and the speech segments long enough, about 20 to 30 seconds, it will provide us pretty good results in around 5% error rate. So, in order to do language identification, we want to take the audio of the recorded call and say what language it was. So we can see it as a compression problem. So from the one side, we stream megabytes of audio, and from the classification, we have a single integer that indexes us the language we use. So in the middle, we have a standard feature extraction and classification. For classification, we can, for the classification side, we can take a simple logistic regression. And for the feature extraction, we have two steps. First step is a MFCC extractor. It's a pretty standard feature extraction scheme. What it does, it extracts features out of frames of pretty short durations, about 25 to 30 milliseconds. Then, I vector extraction compresses all the data, and thus we can dispose the time dimension. It's very interesting, so I will talk about it later. And about the pre-processing state, we have to remove the silences and do some stuff to segment the data so we can use it. So, basic feature extraction. It's called Mel frequency capsule coefficients. And what it's done, we are taking short segments of 25 milliseconds, doing some windows on it, doing some Fourier transform to get the energy in the frequency state, putting it through the Mel filter bank. Mel filter bank is a special kind of bank. So you can see that as higher the frequency, the larger the bank. So it imitates the properties of human hearing. So then we just do the logarithm of the values, and put it back from the discrete cosine transform that does two things. It brings it back from the frequency plane back to what we call capstorm, and decorrelates the values. So if we take the raw audio, a frame of about 25 milliseconds, it's about 400 samples. After Mel filter bank, we'll have only 40 samples. And after we do discrete cosine transform, we throw everything below 13 first coefficients. So what we have is a compression from 400 samples to about a feature vector of 13. So now we want to dispose of the time dimension, because every talk has a different duration. iVector will provide us this ability, but I have to explain it a little bit before that. So we see that we cut our speech into the frames, and for every frame that has some speech activity, we can have a feature vector. It's marked as a red point. From that feature space of dimension, let's say 13, we can model our feature space with regular GMMs. And this is an unsupervised training. Next, what we can do is, when we have all our feature space modeled, we took specific language and adapt the GMM centers to that specific language. So this way, we can get some kind of transformation that provides adaptation of our specific language. And from that, we can take all those means of the Gaussians and create a super vector, which is very long. And the next step is we want to remove its dimension. It is regularly done with probabilistic linear discriminant analysis, but from our point of view, all we want is just to remove that duration. So we are looking for some projection that will remove our dimension while containing our information. So what we have here is speech is going in, and we don't care about the length of our speech in time. We take all those feature vectors and compress them to the I vector. So as another feature enhancement, what we are doing, because speech is very variable, is a signal with high variability. So what we want to do is to normalize it, have capsule mean and variance normalization is a standard normalization procedure. So we just take a mean of all the data and its variance, make it 0, 1. And vocal triad linear normalization is a procedure that compensates for the different pitch of the people. So like men have a lower voice and women generally have a higher voice, while we can normalize these differences by adjusting the frequency axis of the filter of the male filter bank. So let's see some experiments. Now we know the terminology. Sorry. So what data do we have? Although we have thousands of data recorded, we don't know which languages our users speak and what calls were recorded in the different language. So first of all, we had a hard time to find those recordings. After we had an initial 500 recordings, about 500. We took about 200 to the test, and the separation was done by the representatives. So if one representative is in the test, it definitely wouldn't be in the train. Now the training flow. We take the LRE-07 recipe, speech segments of 30 seconds, and start with that. We have two variants, one with the GMM front end for the I vectors, and the other one with DNN front end to the I vectors. DNN was trained on the English data, so it knows what the phonemes is, and the output, the posterior probability of the deep neural network was taken as an input to the I vector extractor. So the next difference between version 1 and version 2, we have VTLN in the GMM training and no VTLN in the second version, because the logic is that the DNN is smart enough to compensate for the differences of the speakers. First, errors. And we see that English and Spanish works okay, and the Hebrew is okay, not very good. The same picture in the DNN recognizer, but we see the GMM system is pretty much better than the DNN. And the explanation is because the DNN is working on the English part of the speech. And when we put in French or Hebrew or Spanish, we were having the system to recognize the phonemes it didn't see in the training. So the DNN is not working well on the data it didn't see previously, obviously. So because we didn't have any system to build the DNN properly, we have to throw it away. So the most important thing in that iteration is that with the help of the previous recognizer, we could find a good candidates for the different languages. So everything that wasn't recognized as a good English was put as a candidate. People was looking at those recordings and labeled it accordingly. Another thing that we have done, it's we have reduced drastically the amount of hours that we have put in the training. And we have reduced also the segment sizes to 20 seconds. So that the training is now in the configuration. We have a VTLN, CMVN, and GMM-based I vectors. So we have 4 languages, and it works strange because Hebrew fell down to about 70%. It was better before. What happened? And after analyzing the training data, I have realized that for some reason, several recordings that were marked as Hebrew were actually French, and that contaminated the model of Hebrew. So those results are not unexpected, are not totally unexpected. So what we do next is I have considered the influence of the I vector dimension on the accuracy of recognition. And as you can see, no matter what, the I vector dimension in our case doesn't change much the results. So we prefer to stay with a lower dimension because it gives us less time to the translator for the training and less time for the recognition. So the following iteration, it was the last one. We have corrected some labels, and we have added some languages. We have adjusted the amount of hours to the train. We have I have left the 20-second segments, and totally we have entered 245 hours into the training. If you see on this table, we have about 780 hours. So most of the recording is not in the training. This is where I can say it's the more data is not helping you to build a better model, because the data of the same call is not different enough. The diversity of the data doesn't provide you anything new. So interesting. You usually don't see this kind of information in any field. That usually, as you pour more data to the recognizer, it's always improves. Okay. So overall, we see a good recognition on all languages besides Italian. And I want to. It was pretty interesting. Why we have not so good results on Italian. And if you go back, you see that in the Italian we have only 10 representatives that we have trained on them. So what our model have learned, the same representatives, we have now detecting those representatives. And any other data it's not English, it's not language, it's the representative. Now we can define and find those representatives in any call, but not the language we are speaking in. So distribution of scores, we can see that in Spanish, French, and English, our scores, when we have a true recognition, they are much higher. It's in the area of 80 and from 80 to 1. And when we don't recognize them good, the scores are pretty low. So it's a good sign of model. So when you have a model and you build a graph like that, it will provide you some information about how you can do. And previously we had always talked about segments. This is what we go on. If we take 10 segments and cross it all over. So when you take 10 segments and project from the call, obviously you have a better amount of recognition. And this way we have found that label that wasn't actually English, because it was half a conversation was English, half conversation was French. I don't remember exactly. But and the Italian calls, yes, we have we don't have much Italian calls, so we don't recognize them good. So summary. First of all, Caldi is a very good framework, and it's provide many examples. You can do it at home with your data or the publicly available data. It is possible to do a language detector. It's not that complicated, but you have to be careful. Diverse data is better than just small data, and you have seen that in some application. And the weak data detector that we had previously helped us a lot to find good examples for further labeling. This is my talk, and thank you. And if you have questions.